I am the Director of Marketing here at Photonic, and I am so pleased to introduce you today to our webinar, A Deep Dive into SHYPS, Photonic's Error Correction Code Family. Without further ado, I am honored today to be able to introduce two of my fantastic colleagues. Alex Malcolm is a Senior Quantum Error Correction Researcher at Photonic, and Andrew Glaudell is a Staff Quantum Error Correction Researcher and the team lead of our fault tolerance team. You are in good hands with both of them, so Alex and Andrew, I will let you take it away.
Thank you. So yes, today we're going to be taking a deep dive into Photonic's new QLDPC code family, in particular looking at the SHYPS codes, which stands for Subsystem Hypergraph Product Simplex Codes. So it's going to be a fairly technical talk. In particular, we'll see some technical details of how logic is implemented in these codes, as well as some of the methods and results from the extensive simulations we've done. But we'll also spend some time on motivation at the beginning, in particular thinking about the design decisions that led us to these codes. So we're going to be working from our recent archive paper, Computing Efficiently in QLDPC Codes, but I'd like to note that there are a great deal of resources available online at photonic.com, much more accessible resources. So we have a press release, a nice white paper with lots of pictures, and we also have some sort of reactions from leading quantum analysts about these codes. Okay, so a summary of what we'll see today. Well, we're going to be introducing the SHYPS codes, a new code family which we think genuinely will help accelerate the timeline to useful quantum computation. So I'm sure everybody is aware that for commercial applications, for example, breaking encryption or running interesting chemistry simulations, we're going to need a framework for correcting errors in noisy hardware. The traditional approach, of course, to use an error correction code, and even more traditionally, to use the surface code family. So this is a well-known family, highly studied, many very interesting properties. For example, it only requires nearest neighbor connectivity, which means it's kind of appropriate for many different qubit architectures. The downside being incredibly large physical resource requirements. So if we're talking about a surface code patch that we might use in practice, we're looking at 3 to 10,000 physical qubits per logical qubit. And it's these sort of very large overheads that have put some of the kind of projections of when we'll see real quantum quite far into the future. So quantum low-density parity check, QLDPC codes, these emerged a while back, holding a significant promise to reduce these overheads. And despite a real flurry of activity in the last few years, they've still predominantly been studied in the context of quantum memories. So it hasn't been known how to perform quantum logic efficiently in these codes. So this is sort of where Photonic comes in. We wanted to address this problem, design a new code family with efficiently implementable logic as the core consideration. This leads us to the SHYPS codes, bringing, hopefully, quantum applications closer. The downside to the SHYPS codes is that they are only available to high connectivity quantum architectures, but thankfully, that's exactly the kind of hardware that we're pursuing here at Photonic. So a sort of summary slide about these new codes. They are the first QLDPC code with a provably efficient and fault-tolerant logic implementation, here specifically looking at the Clifford group. So the Clifford group is a very important family of unitary operators needed to compile arbitrary quantum algorithms. And we wanted to focus on the Clifford group specifically because there are more general methods for accessing that sort of additional gate to complete your universal gate set. For example, magistrate distillation or cultivation, and injection that might get you, say, a T-gate. But with this efficient and fault-tolerant logic that matches speeds of surface codes that we see with SHYPS, we have a much reduced physical overhead. So on the right-hand side, I'm afraid I don't have a pointer, but I'll use my words. We see sort of the first instance of an interesting SHYPS code where we encode 9 logical qubits in 49 physical qubits. And this presents some savings against sort of 9 copies of a surface code with comparable distances. But these savings increase, of course, as you sort of go through the SHYPS code family. So for a kind of comparable surface code, maybe something like distance 30 you might use in practice, we see a 20 times qubit reduction by using an appropriate SHYPS code. We also have some single shot properties. So if you're familiar with the syndrome extraction process in the surface codes, if you have a D by D patch, you typically repeat syndrome extraction order D times. In the SHYPS codes, we can do this once or a constant number of times, again, yielding kind of great speed ups 30 times if you're looking at around that distance 30 mark. And so then the last thing I'd like to mention here is we've extensively stress tested the SHYPS codes. What we understand to be probably the most advanced logical simulation under circuit level noise in the literature. So it seems like these codes will work in practice as well as in theory. Okay, so before we sort of get to the SHYPS codes themselves, it's nice to motivate how, kind of the path we took there and think a little bit about code design. There are a number of different facets of code design, things you might want to consider. I've kind of put them in 4 groupings here. The first one, physical to logical qubit ratio, this sort of being the first sniff test of whether a quantum code is going to be any good. Obviously, this kind of gives you a sort of overall picture maybe of how much your system is going to cost in terms of physical resources. Lower ratios bringing down the cost of large systems. And this is where a lot of effort has been focused in developing QLDPC codes recently. In particular, we've seen the introduction of good QLDPC codes, where we've got constant qubit overheads, which is amazing, and also linear distances. So these are really nice codes. Of course, in computation, both time and space matter. And these good QLDPC codes, we've sort of seen reduced physical resource requirements, typically coming at the cost of increasing time for computation. So this sort of brings us on to point 3, efficient and fault-tolerant logic. This might be something you want to prioritize in your code design, and it's exactly what we have prioritized. So this notion is going to come up quite a lot. Efficient logic, in particular, efficient Clifford logic in QLDPC code. So let's try and nail down exactly what we mean. Well, we want to implement an arbitrary logical Clifford operator, so say on k logical qubits, and we want to break this down into a low number of physical Clifford circuits plus low number of physical measurements. More specifically, if we consider the depth required to implement a worst case Clifford operator, we want this to have constant scaling with respect to the number of logical qubits involved. So this is sort of summarized by this fractional ratio here that we call the Clifford compiling ratio. We look at B blocks, each consisting of k logical qubits, and we think about the worst case physical depth to implement an arbitrary Clifford. And we want this to be a constant multiple of B times k, of the total number of logical qubits. The reason we sort of landed on this Clifford compiling ratio and this constant target is because this would then put us on par with the best known cases for unencoded qubits. I think some of the most recent work is due to Maslov and Zindorf, where they consider unencoded qubits implementing arbitrary Cliffords as sequences of 2 qubit gates. And what they find is they achieve a Clifford compiling ratio of 2. So if we can get a constant ratio while using a code, we're sort of on par with the unencoded case. Then, of course, we can think about what it means to be inefficient. This simply means that your depths are growing faster than the number of qubits within a code block or faster than the number of code blocks themselves. So this sort of ratio captures sort of the many code block scale and the individual code block scale. Okay, so how do we go about implementing logic? There are a few different flavors, a few different methods for implementing logic in QLDPC codes. One of them we call generalized lattice surgery. So this is a measurement-based scheme that sort of borrows techniques more commonly seen with the surface codes. How does this proceed? Well, the first thing we do is we enact measurements of joint logical Pauli operators. We then compile these into elementary Clifford gates. So for example, isolated C0 or single qubit Hadamards. And then we compile these isolated gates into more complex operators. The most recent work, I think from last year, due to Crossan authors, show that you can do these logical Pauli measurements in order D overhead in both space and time, D here being the minimum distance of the code. And then when it comes to compiling more complex operators, well, if we assume a very high degree of parallelization commensurate with surface codes, which may or may not be possible for your QLDPC code of choice, we're going to require order k cycles involving a constant number of measurements. So we get a total circuit depth of order k times d. So this sort of fails our efficiency criteria we saw earlier, because we got this scaling with the code distance. What about an alternative option? Well, we could consider just direct unitary implementations. We want nice, low-depth physical circuits that enact some well-describable logical operator. And I like to think of the standard transversal CNOT here as the gold standard. Why is this great? Well, on this picture on the right-hand side, we have 2 code blocks, each consisting of 4 physical qubits. And we know that if we just do this pairing up with physical CNOTs, a nice fault-tolerant depth 1 circuit, so it couldn't really be any better, we get a nice logical operator out. In particular, we get a single logical operator between logical qubit 1 and 2. If you're familiar with the different representations of these operators, you'll know that a CNOT circuit is completely characterized by how it acts on Pauli's, in particular on Pauli X. So that leads to a very nice linear operator description, which we'll be using. So this is the matrix here in blue. For this 2 logical qubit case, we get a 2x2 matrix. And in general, a cross-block logical operator, where we have all the logical controls in one block and all the logical targets in another, will have a nice sort of block upper triangular form. We'll see a lot of this later. Okay, so this is great, right? Every CSS code has this implementation available, but it's just one, right? It's just one nice logical operator. We're going to need far more if we're going to achieve sort of efficient compiling. And we can quantify this. How many do we need? Well, let's suppose we have some collection of low-depth, nice circuits. Let's say we have A of them. We can call these generators. We can use them to generate, compile a large collection of Clifford operators. But this number, A, how many logical operators I have in my bag to choose from, is going to put a hard limit on how efficient my compiling can be. Simple counting argument kind of gives you a guide here. If we think about k logical qubits, the Clifford group has 2 to the 2k squared elements. So if we think about stringing together choices from our bag of logical generators, strings of up to length d, we're going to yield at most a plus 1 to the d unique operators. So it kind of falls out pretty easily then that if a is not growing exponentially in the number of logical qubits, we simply won't have enough generators to achieve efficient compilation. So here, D being order K. So this is kind of like a nice recipe for success, I guess. We want to construct an NKD quantum code that has 2 to the K, this exponential number of short logical operations. But we'll note that this is a necessary, not sufficient condition. So we still have a couple more steps. We've still got to prove that, well, my bag of generators does actually generate the Clifford group. They've got to be fault tolerant. And then we also have to demonstrate that we get the asymptotic scaling that we want in the worst case. Perhaps I should mention, actually, that we will typically expect the worst case depth required to implement a logical Clifford to be the average case. So it's really worth thinking about this, this case here. I am a group theorist by training, so any chance to use symmetry is always a win for me. We can access a greater number of nice physical implementations of logic by using symmetry of the code. So code symmetries are simply qubit permutations, physical qubit permutations. We call these automorphisms, and they preserve the code. So you would check that they preserve the stabilizers or the gauge operators, depending on what flavor of code you have. And they're a really promising foundation for computation because they can provide non-trivial logical operators implemented by either low-depth swap circuits or by relabeling physical qubits. Here's actually a really nice way that you can use a permutation automorphism in conjunction with the transversal CNOT we saw earlier. If we conjugate it, we produce a different logical cross-block CNOT operator. So on the far right here, we see a matrix description which has this nice upper triangular form again, but here the upper right block C will be more general than previous. But the win here is that basically at the physical level, it's still fault tolerant and still depth one. So more symmetries means more of these nice implementations. It does, of course, mean that we will require more connectivity. So qubit permutations, they preserve the X and Z type of our checks. So they will only implement logical CNOTs, but there are other types of symmetries called ZX dualities that implement different flavors of Cliffords, for example, Hadamard's or diagonals. Right, so we've done our setup. We're now ready to introduce the SHYPS codes. Essentially, we went in search of a really symmetric code. We want a code with this exponential number of symmetries, hoping that we'll get an exponential number of nice short logical operators, and then hoping further that these will efficiently generate the full Clifford group. And of course, there are a number of different ways you can construct a quantum code. We like the subsystem hypergraph product that takes 2 copies of a classical code, say with parameters NKD, parameterized by a parity check matrix we call H here, and it produces a quantum code with n squared physical qubits and k squared logical. I think the nicest way to sort of see this code construction is this diagram on the right-hand side. My black dots here are my physical qubits arranged in an n by n grid. And then in terms of the checks, what we find is that one copy of the classical code is sort of defining the X-type checks, the X-type gauge operators on rows of the qubit array. And then another copy of the classical code is defining the Z-type checks on the columns. The really nice thing about this code construction is that if you have classical symmetries, so classical automorphisms, these lift to quantum symmetries. So we can achieve a permutation of my n by n grid by simply sort of doing a row permutation and a column permutation. This is a really nice construction, and the natural thing then to do is to say, okay, well, let's use the subsystem hypergraph product construction with an incredibly symmetric input. And so that's what we did. We chose the well-known simplex codes. So these are a classical family dual to the Hamming codes. And this produces the subsystem hypergraph product simplex codes. So this defines a code on R squared logical qubits. And it indeed has this exponential number 2 to the 2 R squared symmetries that we desire. And then I guess the last thing I'll note on this slide is that because each X and Z check has weight 3, regardless of which code in the family you take, this is QLDPC. Right, so we have the necessary symmetries in our code. But what's sort of even nicer is that it's very easy to characterize the logical operators induced by the symmetries. If we think about logical CNOTs, we take some pair of symmetries, sigma 1, sigma 2, apply that to the row and the column. We induce a logical CNOT that has a nice matrix description. It's simply a tensor product of 2 R by R invertible matrices, M1 tensor M2. And in particular, we have so many symmetries available to us for any choice of MI invertible that you please, you can find the corresponding symmetry that induces it. So this is great. This is a really phenomenally large amount of logical operators distinct that can be induced from these automorphisms. I guess the one thing I will mention is that the MI has to be invertible. So that's going to be important for later on. What about Hadamards? Well, if you're familiar with the work, I think of Breukman and Burton, you might recognize this construction. This is a Hadamard type fold transversal gate. This utilizes, in fact, I think I missed something here. So this utilizes an additional symmetry of the code, which I forgot to mention. Let me go back here. We have, in addition to sigma 1 and sigma 2, we have a ZX duality. So this is a symmetry that exchanges the X and Z type checks. We call it tau, and it essentially behaves like a reflection along the diagonal of the qubit array. Okay, apologies for missing that. It's going to come up a bunch, so it's good we covered it. We use it exactly in the construction of a logical Hadamard. So what we do at the physical level is we lay down a Hadamard gate on every physical qubit. We then implement the swap corresponding to this reflection tau across the diagonal, and that gives us a logical Hadamard operator which actually very nicely at the logical level completely mimics what we saw at the physical level. And then lastly, we could consider diagonal Cliffords. So these are Clifford operators built from phase gates and CZ gates. If you're familiar with the symplectic representation, we know that we can describe these by a symmetric binary matrix. Okay, so let's think about how that works in our codes. Well, we take one of the classical symmetries, sigma, we tensor it with its inverse. We also compose it with this ZX duality tau that indeed produces a symmetric permutation matrix. And we use the entries of that matrix to basically tell us where to lay down physical S and physical CZs. So on the left-hand side, we have an example, which is actually sigma being trivial, so sort of just the tau. And what we find is that fixed points of the reflection tau, i.e. the diagonal qubits, we lay down an S gate. And then if we have any pairs that are connected by this reflection, we lay down a CZ that connects the two. And this is a depth one implementation of a logical diagonal gate. And the logical action is very easy to characterize as well. We see it simply a tensor product of M tensor M transpose with a logical version of this reflection added on. And for any choice of invertible M, we can find an appropriate sigma. So this is great. Again, we have a very large number of distinct logical ops induced by symmetries. Okay, that was a bit of a whirlwind characterization of some of the logical Cliffords we get in the SHYPS codes with nice depth one physical implementations. The question now is, okay, well, are they fault tolerant? That's actually a fairly straightforward exercise here. With the subsystem hypergraph product construction, what we find is that we can choose a basis of logical Pauli's supported on lines. So a little bit like checks, we have Pauli's supported on rows and columns of the qubit array. And then all the constructions I just outlined, they may involve 2-qubit gates, e.g. CZs, but they never have full support on a line. So what this means is the circuit distance is preserved. Our applications are indeed fault tolerant. That they generate the Clifford group is a little bit more complex, but really it boils down to, can you generate C0 circuits? We saw this picture earlier of the circuit diagram of the cross-block logical C0 operator and how it corresponds to this matrix description of an upper triangular block matrix with a C in the top right block. What we find from what we just outlined is that we can choose C to be any choice of tensor product of invertible matrices. Okay, and then if we think about how these circuits compose, it behaves like multiplication of the matrix representations, and that in turn behaves like addition of the C factor. And then simply what we find is that we can achieve any K by K matrix, so we can generate the full algebra by adding together these tensor products of invertible guys. And essentially what this gives us is a way to generate all logical cross-block C0s, and then you're kind of off to the races, really. You take the transversal H we saw earlier, you take any choice of S-containing diagonal, and you get the full Clifford group. Okay, so that was sort of step B, I think, of our recipe for success. The final step is efficient generation. I'm really not going to go into much detail here because this is 35 pages of a horrendous technical linear algebra in the appendix of the paper. But a couple of insights. Firstly, we do a natural thing. We break it down into subgroup problems. And then in each subgroup, we then break it down into studying sort of efficient generation at the single code block and multi-code block level. For C0s, as we sort of described, the crux of generation is, can you achieve an arbitrary K by K matrix by summing together these tensor product summands? And in particular, for efficient generation, we want order K to appear in the sum. Now, if we remove the invertibility condition from the tensor product, this actually becomes quite easy. This is just standard methods, tensor rank decomposition, that will give you a sum of at most K potentially non-invertible terms. The real crux of the problem is then turning potentially non-invertible tensor products of matrices into invertible guys. obviously while incurring sort of negligible additional overhead. But that is something that can be done with a whole bunch of fun lemmas. I think an example would be a little bit more straightforward. So let's suppose we have two code blocks in the SHYPS codes. We want to implement a logical cross-block CNOT operator corresponding to a choice of matrix C, which is this 4x4 upper right block in this large matrix. If we use standard tensor rank decomposition methods, because it's a 4x4 matrix, it will break down into a sum of at most 4 terms. But what we find here is we have two that we like, two green consisting of invertible tensor products. So these correspond to our nice depth 1 generators lifted from automorphisms. But we've got a couple of non-invertible guys in there. So you'll just have to believe me that in general, we can indeed break these down while incurring negligible sort of additional summands. And if you're really interested, here outlined below is exactly what you would do for these two red guys. Okay, so this is my final slide. What have we seen? We have seen that indeed with the SHYPS codes, we have a sufficient number of nice low-depth, fault-tolerant logic implementations, and we can use those to generate the Clifford group efficiently. So we can hit all the optimal scaling that we desire for arbitrary Clifford circuits. But not only that, we actually have very nice individual addressability in these codes. So for example, if you wanted just the logical gate S on logical qubit number 1, say, this can be achieved in 6 logical cycles or 6 rounds. So where here each round consists of a depth 1 logical circuit followed by a syndrome extraction round. And we get this for all the elementary Clifford gates. So 8 in the case of H and 4 in the case of C, Z, and C0 gates. In addition to the very sort of high picture, worst case arbitrary Clifford, we also have some nice, more specific results for different families, for example, C0 families or diagonal Cliffords. Okay, so that was a sort of whirlwind tour of logic in these codes, showing how, we expect to use them in theory. I guess I will now pass over to Andrew, who will tell us a little bit more about simulations in these codes and how we expect them to work in practice.
All right. Thanks a lot, Alex, for talking us through all of the logic in SHYPS codes and how we can compile efficiently with them. So that's sort of, again, one piece of the puzzle that we addressed in this work. The other piece that we're kind of naturally interested in next is, well, how do these actual logical circuits perform in practice? So in particular, we'd like to get a handle on, given that we take an arbitrary Clifford and synthesize it in these methods, what is the actual logical performance hit compared to, say, a memory setting? And in order to study this, we'll use kind of the gold standard for addressing the performance of codes, which is just circuit level noise. Okay, so if you are familiar with circuit level noise, this slide will be kind of obvious to you. If you're not that familiar with circuit level noise, this slide probably isn't quite enough to teach you how to do it in one slide, but hopefully it's enough for you to follow along for the rest of the talk. If you're interested in understanding it a little bit better, just read any of a number of recent LDPC papers. They will talk about their implementation of a circuit level noise simulation. But essentially what you're trying to do with circuit level noise is take the kind of general framework of stabilizers and stabilizer error correction and transporting it into the setting of actual, say, Clifford circuits you're running to actually assess the performance of the code. And so in particular, the kind of analog of stabilizers for a circuit level noise simulation are these things called detectors. And so for a detector, you can kind of think of it as trying to not only locate an error in space, i.e. which qubits have errors, but also locating in time. So at what point in my circuit did I have an error? And so there are actually a number of ways to define detectors for a given circuit, in the same way that there are many different ways to define stabilizers for a stabilizer error correcting code. But there is sort of a natural way to define detectors in a given circuit level simulation. And that is, you take a stabilizer measurement that you made at time t, and then you compare it against the value of that stabilizer measurement at time t plus 1. So all this is doing is essentially telling you, did I have an error occur between time step t and time step t plus 1, where that error anti-commutes with the particular stabilizer I'm measuring? It's a little bit more complicated with that. You have to worry about error spread and whatnot in the context of the circuit you're running. But morally speaking, that's what these kind of detectors are trying to tell you. I should note for subsystem codes, which the SHYPS code is, you have to do even a little bit more, which is that you don't directly measure stabilizers, you directly measure gauges, and then you aggregate gauges to give stabilizer values. This is just a little minor bit of complexity on top of things, where you infer the stabilizer measurement result at time t from the gauge measurement results you made at time t. But once you've defined all of your detectors in this way, you can start to create a giant binary matrix H, where you assign each row in this giant matrix a detector, and assign each column in this matrix an error mechanism, where an error mechanism here is something like, say, an X error appearing after some particular, say, Hadamard gate in your circuit. And you will have, obviously, a gargantuan amount of error mechanisms in a circuit, because you'll have an error mechanism for a poly X error happening at one point and a poly Y error happening at that same point, and so on and so forth. Roughly speaking, the number of columns in this matrix scales like the volume of your circuit, essentially. And you put a 1 in the ijth entry of this giant matrix if the error mechanism in column J trips the detector corresponding to column I. Now, by virtue of us having defined detectors in this kind of standard way, and by ordering the list of detectors and the error mechanisms roughly by time, you actually get a very nice structure to this, this matrix. And that structure is something called a spatially coupled structure. It's used a lot in classical error correcting literature to improve decoding outcomes. And we'll see how that's beneficial in a little bit here. But essentially what you do is, to perform one of these simulations, is you flip a bunch of coins, sample errors for your for Monte Carlo sampling. You take this list of error mechanisms that have fired in your circuit, you multiply H on the right by this list of error mechanisms, and this gives you out essentially what is a syndrome for those error mechanisms having fired. And then the goal is to, given this syndrome S without knowing E directly, to use H to decode S to find whatever the most likely error mechanism E hat is. And you will know when you have an error if something called an observable, which is some deterministic aggregation of measurements that you've performed that aren't described by your detectors, if that flips, given that you inferred E hat as opposed to E. So this is how you check whether an error is actually caused you a problem. Okay, so that's detector error models, circuit level simulations at a high level. when you actually go and produce one of these detector error models for, say, a SHYPS code of, so this is, I believe, the 49 qubit SHYPS code and 4 rounds of syndrome extraction, you see this kind of characteristic spatially coupled structure that I described earlier. These kind of boxes in red and yellow here are kind of 1 round of syndrome extraction. And the way that the decoding of these spatially coupled systems works is, rather than having to decode over the entire matrix all at once, you can essentially cover up large parts of the matrix and not do any decoding over those until later in the decoding process. So essentially, you can start in the upper left-hand corner, focus on solving kind of a sub-decoding problem there, and then commit some amount of your inferred error mechanisms in the, say, the earliest part of your decoding sequence, then propagate the outcomes due to those inferred error mechanisms forward, and then essentially slide the set of error mechanisms and detectors you're looking at down and to the right in this matrix. So this is something called a sliding window decoder. It's covered in, I think, a number of papers in the literature at this point. I know Shruti Puri has some papers on it, for example. That might not be a bad place to start if you want to learn more about this. But in particular, it is characterized by essentially 2 parameters, which is how many of these rounds of syndrome extraction are you sort of needing to aggregate and look at kind of all in one shot, and then how many rounds of syndrome extraction are you sort of committing based on. So those 2 integers kind of tell you how difficult each individual decoding problem that you're solving is when you're stitching together the full decoding of one of these detector error models. So sliding windows work in particular very well with small window sizes when you know that your constituent code has single shot properties. So that what a single shot property allows you to do is to sort of solve smaller and smaller decoding problem, choose a smaller and smaller window size on that matrix that I described on the last slide. And in particular, we know these SHYPS codes have single shot properties. So why does a SHYPS code have a single shot property? It comes down to the fact that simplex codes have single shot properties. Let's recall that the gauges that we actually measure for SHYPS code come from simplex codes on each of the lines, right? So like the very first column of this array on the right here has gauges that are measured along a line. Now, the actual measurement outcomes of these are constrained to some extent. And so the reason this happens is because if you look at a simplex code, in particular the gauges that we're measuring to infer the the gauges of the simplex code or the SHYPS code, the gauges that we measure produce code words. The resulting gauge measurements we get are code words of the dual of the transpose of the code that we're working with. So the transpose code of the simplex code is in fact itself a simplex code, and the dual of the simplex code is a Hamming code. So that means that when we get a sequence of gauge measurement results for a given line of this code, those gauge measurement results correspond to the code words of a Hamming code. Now, a Hamming code is a code with distance 3, and that means that it can correct, without knowing a priori, exactly one error in a gauge measurement result. So any one gauge measurement result along a line is correctable. Now, this is all at the sort of capacity level, but it turns out that when you transport like all of these things to the circuit level, essentially all of this redundancy is maintained. So you have redundancy in these gauges, and you can make use of it in your decoding. And so what this allows us to do is to use smaller and smaller sliding window sizes. Okay. So to see that in practice, all you need to do is crack open, say, STIM, and start setting forth one of these memory simulations and choosing different window sizes for a sliding window decoding of one of these simulations. So in particular, you can see that for this 4994 code, you really can get away with essentially the smallest possible sliding window size, which is like a 2-1 sliding window, in order to decode, and you get the same performance as if you were decoding over 4 rounds like you normally would for a code like this. So that's a great sign. In addition, you can go to bigger code sizes and again, use 2-1 sliding windows, and you see that there's no drop off in performance, or at least very minimal drop off in performance from doing decoding over the full graph. And then we can also kind of compare against surface codes at comparable sizes. And so we see, for example, for the distance for surface code versus the distance for simplex code, that the logical error rate and the physical error rate, or the logical error rate performance of the code is essentially the same at a much reduced qubit count. Similarly, if you were more interested in getting more logical qubits for the same physical qubit count, you can also get better logical error performance for a fixed number of physical qubits. We see that the 225 qubit SHYPS code is shifted left from the surface code, so you're losing a little bit in pseudo threshold for the distance 8 versions, but you're doing this with, say, almost a factor of 10 fewer physical qubits. All right, so that's memory in these codes. But we said we're interested in assessing the performance when you're actually doing logic. And so when we're actually doing logic, we need to slightly change the simulations that we're doing and how we set them up. So recall that in a memory setting, all we're doing to define detectors to get this nice kind of spatially coupled structure is we're comparing the previous result of a stabilizer with the current result of a stabilizer for a fixed stabilizer. But this no longer works when you start performing logic. So why is that? Well, Clifford logical operators, when you look at what they do to stabilizers, they don't actually fix stabilizers. They fix the stabilizers as a set, but they don't map individual stabilizers to the same individual stabilizers necessarily. A very easy way to see this is if you consider, say, like the transversal Hadamard operation that Alex described, where very clearly that is mapping these like X stabilizers to Z stabilizers and vice versa. So really, what we should do is we should think about where stabilizers are mapped by a given logical operator and define our detectors that way. So if we take a logical operator which maps stabilizer I to stabilizer J, then really we should compare the value of stabilizer J at time t+1 to the value of stabilizer I at time t, because there's no reason that the stabilizer value of stabilizer I needs to match itself in adjacent time periods when you're performing this logical operator. So all you need to do to define detectors for your logical operator, given that you've performed a logical operator L here, is to just compare each stabilizer's value at time t+1 to its pre-image under the action of L at time t. And mind you that the logical operator L here, it doesn't need to have a pre-image that is precisely one of the stabilizers you measure, but it will always be a linear combination of these stabilizers that you measure. Okay. So in order to set up a deep circuit level logical simulation, all you need to do then is to interleave rounds of syndrome extraction with one of these depth 1 logical circuits that Alex has described. And then you zoom in on kind of 2 adjacent rounds of syndrome extraction straddling a logical operator and define your detector based on the action of the logical operator you've performed in that moment. And you can then kind of take a gigantic circuit and do all of this aggregation and feed it to, say, STIM, and out will pop a detector error model. So we ended up doing this for a randomly sampled logical Clifford, which we synthesized. I'll talk about that in a moment. But just to give you an idea of the kind of sizes that we're dealing with here, this results in a detector error model where the number of detectors is listed here at a little over 10,000. I believe this one had like 10 million error mechanisms or thereabouts. So the actual size of the matrix in memory was on the order of like somewhere between 10 and 100 gigabytes. So maybe don't try it on your laptop, but still within the realm of like you can design a computer system to handle that. For more complicated simulations, there's plenty of stuff you can do. It's just you can't just feed it to STIM directly like that anymore. But the actual simulation that we ran, in order to generate it, we generated a random Clifford on 18 qubits. That's because we're going to do a simulation on 2 code blocks of this 4994 code. So 18 being twice 9. We take that random Clifford we generated and we synthesize it using the methods that Alex had described in the first section of this talk. For technical reasons, we did this up to in-block C0 circuits. If you've read the paper, you know that the way we talk about doing in-block C0 circuits is ever so slightly different. It involves an ancilla patch, and we didn't want to have to deal with the headache of also simulating the ancilla patch. So really, you could think about this as like a random Clifford coset of the Clifford group modded out by a particular subgroup. It's still a deep Clifford with lots of interesting action on polys. So it's a pretty good proxy for a random Clifford. And so you synthesize this thing, you build the detector error model of C interleaved with these syndrome extraction rounds, and then you essentially play the movie backwards. So take whatever circuit you synthesize for C and then implement its inverse in subsequent order. And then you just feed it into your favorite decoder. So here we used a 3-1 sliding window using just kind of bog standard BPOSD. And I want to emphasize that the plot we've generated here is there really was not a lot of artistry to try and massage this to get data points that look nice. This was basically like, let's take our bog standard BPOSD decoder, jam it into jam our giant detector error model matrix in a sliding window, decoder using this BPOSD thing and see what pops out. So I'm pretty sure that with additional fidgeting, you can drive the pseudo threshold you're seeing here even further to the right and make the logic simulation even closer to memory. I should say that what you're seeing here is kind of a per round logical error rate. So the logical error rate is obviously going to be worse the deeper you go, kind of no matter whether you're doing memory or logic. But what we're seeing here is kind of a characteristic error rate you should expect per depth 1 logical circuit that you implement. Okay, so as Alex described, we introduced this family of really highly symmetric QLDPC codes. We introduced them motivated by the idea of what sort of things would you need to have enough transversal gates to efficiently implement the Clifford group. We showed that the resulting logical Clifford depths are asymptotically on par with unencoded Clifford depths. We showed that these things actually have good individual addressability as well. And then performed some very deep logical simulations based off of these things, showing that their performance is on par with memory. Now, we don't see these codes so much as the end of the story, but sort of a beginning of the story, if you will. And so I think there's a lot of work that would be really interesting, both for us or the community to do as a kind of follow-on to this work. So for one, we don't show that these codes have a threshold, for example. So you might wonder, like, do these codes have a threshold? Our expectation is that they probably do not, for the same reasons that the Bacon-Shor code just doesn't have a threshold out of the box. What is interesting, though, is that there's this recent paper about how to give the Bacon-Shor code a threshold. And so one might very much wonder whether you can do the same thing with these codes. So that's an interesting thought. We could certainly look at other codes or code families with analogous properties. Remember this being that the number of kind of cheap logical circuits scales exponentially in the number of logical qubits. You can start to explore the bounds on the achievable code rates, distances, etc. for such codes. I think there has been some work along these lines in the last couple of months, kind of looking at the possible rates for codes, given that you demand certain things about individual addressability and whatnot. And then one really important thing to do would be to perform some rigorous QRE on, like, what does the actual outcome of doing logic this way versus, say, lattice surgery or its most modern form look like in practice for things like Shor's algorithm. Like, which one comes out on top? Is the right answer kind of something that's using both? A little bit of one, a little bit of the other, some kind of hybrid approach? Who knows, right? I think, interesting work to be done. So with that, I have nothing more to say. So I'd be curious what kind of questions we had crop up during the talk.
Back to help you with that.
Monica, your sound isn't working.
Oh no. Well, that's gonna make
now it's working.
Okay, a little delay there. Yeah, we're getting a bunch of questions coming in right now. So I'm just going to start with one of our first ones received from David here. He was asking how many gauge operators are needed to make up a stabilizer operator of the code. It's a two-part question. And actually, how many gauge operators are there in the 4994 SHYPS code in total?
Yeah, okay. So the number of gauges that constitute a stabilizer is D, if the distance is D. So it's not unlike the Bacon-Shor code in that sense. The number of gauges you actually measure in a given code is exactly the same as the number of physical qubits in the code. So if it's the 49 qubit code, you measure 49 gauges. Or sorry, you measure 49 X gauges and then 49 Z gauges. So twice the number of physical qubits.
Okay, thank you. Sorry, I'm just trying to read through the questions here. This question, from from Gotham. Sorry if I'm saying your name wrong. Can we draw parallels to how symmetries are leveraged in classical error correction, or are there unique quantum-specific advantages or challenges in the concept of automorphisms?
I guess I could take that one. It's very similar. So the C0 induced operators we saw from symmetries, I described that if you apply a permutation of the rows and the columns, you get this tensor product of invertible matrices. The sort of M1 invertible matrix is exactly the linear transformation that you induce on the classical parity checks. So there really is a direct relationship between the classical automorphisms inducing, I guess, what you'd call a classical C0 operator and the quantum version. The difference, I guess, being that because in the quantum case we have two flavors of checks, we have our X and Z checks, we get these additional symmetries, the ZX dualities, which aren't standard permutation automorphisms like you would see in the classical world. And that gives you access to the diagonal Cliffords. So there is a lot of similarity, but yeah, there are some extra things you get in the quantum case.
Great, thank you. Okay, next question here. I think I'm just going to stop attempting to say names because I'm just going to say them all wrong. But can you comment on the stabilizer weights for subsystem codes? Can you still think of them as QLDPC?
Yeah, so that's a good question. The stabilizer weights do grow as the codes get bigger. The gauge weights do not, but the stabilizers do. The stabilizers don't grow linearly in the size of the code. They grow, in this case, they grow quadratically. But it turns out that the performance hit isn't too bad. So for example, like I think when you look at like the Bacon-Shor code, for example, even though the stabilizer weight is growing as the codes get bigger and bigger, and there's this kind of famous result that you kind of have an optimal Bacon-Shor code size for any given physical error rates, when you actually look at the logical error rates that you get for like reasonably sized codes, they really are kind of like good logical error rates for the physical error rate that you're implementing, and these codes are not dissimilar in that respect. So you really, even though you would like a thing where it's like my code getting bigger is always a better choice, really what we care about from a practical standpoint is, given I have a certain physical error rate, like what is my logical error rate? And in particular, can I hit a logical error rate that is sufficient for like the actual algorithm I'm running? So 10 to the minus 15 or something for Shors. And the answer can often be, yes, I can hit that even though my code doesn't have a threshold.
Amazing. Well, thank you so much. That takes us to time. We don't want to go over time for anyone. So thank you for all the questions. Andrew, Alex, thank you so much for joining us today. If anyone would like to see the white paper or the scientific paper is available on arXiv, a preprint of it. They are also both available in the handout sections of this webinar here. And when the webinar closes, you will go to our blog announcing this, where there's some more animations and videos, as well as links to all of those documents. So thank you so much for taking the time to join us at our webinar today. And we look forward to hopefully having you join us on our next one. Thanks again, Alex and Andrew.